So, good evening, everyone. Good evening, everyone, and this is week 8 assignment solution session for the course Bonds and Bands in Solids. So, today I'll be taking questions for assignment 8, and the questions are as follows. According to Bohr-1-Leumann theorem, which one of the following statements is incorrect? So, to understand Bohr-1-Leumann theorem, one has to understand what it is. So, what Bohr-1-Leumann theorem states is when statistical mechanics and classical mechanics are applied consistently, then thermal average of the magnetization is always zero. So this states that the magnetism cannot be accounted by classical mechanics, neither by statistical mechanics. Okay, only quantum mechanics can explain magnetism, which means that magnetization is purely a quantum mechanical phenomena, which is now in this the magnetization is a quantum mechanical phenomena. It's correct. Classical mechanics cannot explain paramagnetism, which is also correct, and average of magnetization is zero when electrons are treated classically. That is also correct. The classical partition function is independent of the applied magnetic field. Yes. Magnetic behavior of free electrons is predicted to be same. No, because classical mechanics cannot explain the magnetic phenomena. So the correct option for the question 1 is A. Now the next question, that a free electron is moving in a circular path on application of an external magnetic field of strength B is equal to 0.1 Tesla. Now the cyclotron frequency is given by EH by M. Now value of charge of electron is minus 19, given to the value of H or value of B is 0.1 Tesla, and where mass of electron in kg is turned out to be this. And if you evaluate, let's say you collect the tensile 10. Okay. Yeah. So this would account to 16 divided by 9.1 into 10 raised to the power minus 31 plus 10, and the 16 divided by 9.1 would be 1.76 into 10 raised to the power 10 radian per second. Now we move on to the question number 3, which is an electron in a solid is orbiting in an orbit in the plane perpendicular to the applied magnetic field. If the differential of the energy of electron with respect to the area of orbit is ds by dE, the cyclotron frequency is given by. Now to understand this, let's say we have the direction of magnetic field to be H in this way, and now we are taking the electron orbit in this manner. Let's say electron is moving in this way, right? And so electron is orbiting in this way, which is perpendicular to the plane of the applied magnetic field. Now differential of the energy of electron with respect to area of orbit S is this. So let's say S is the surface area of orbit. Now to understand this, let us consider the force experienced by this electron. Now force experienced will be given by Q V cross B. Now charge on electron is negative, V cross, now instead of V we are applying H, and this is force here. Force is nothing but the change in momentum with respect to time, and it can be written as dP by dt is equal to minus E times V cross H. Now momentum in quantum mechanical sense can be written by H bar K. Therefore H bar dk by dt is minus E V cross H. Now if one let me take a separate page to this. Now if one considers that the electron which was moving, so in moving the velocities would be this way outside, and let's say it is V is nothing but V perpendicular we are talking about. So this V perpendicular is in fact at 90 degrees to H, and V cross H can be modified as minus E V perpendicular H sine of 90 degree. Sine 90 becomes 1, and I think I just missed a term C. Wait a second. C. So now V perpendicular itself, that we are there, that the velocity of electrons, V perpendicular is given by gradient of energy surface. So V perpendicular is nothing but the gradient of energy. Now we are talking about K states, and so putting this value of V perpendicular in our earlier relation, what we get, dk by dt is minus of EH divided by, now at this H cross going down with H cross, and we had an H cross earlier, became H cross square C delta EK. Now to find out this cyclotron frequency, what we can do now, cyclotron frequency, let's say, is this, which can be found out by T, is given by 2 pi divided by T, where T is the time period for one oscillation of the electron in the orbit. And to find time, what we can do, we can integrate this equation. So time total would be total closed loop integral of dt, which can be written as follows. Now just rearranging this equation, H cross C divided by EH closed integral of dk. Now we have del K. Now also there is another relation, that del KE is related to delta K perpendicular divided by del E, and therefore the total time period we have with us becomes H cross E by 1 by E integral del K perpendicular dk. Now if you look at this, then let's say this was the direction of magnetic field, and we were taking this circular orbit. Now another orbit of smaller circumference, if we take, and let's say we're taking a point here. Okay, so this distance of this distance, just take it in this way, this becomes outer orbit becomes k plus dk, inner orbit is k, and the width of this orbit is nothing but delta k perpendicular, right? Just let me this is not a clean diagram, let me just draw it neatly, and in fact let me draw towards this side. Okay, so this becomes k plus dk, inner is k, or I think there is a small mistake that I'm making here in drawing the diagram. This distance is k, and electron when moved to next position becomes k plus dk. And now after some time, k to k plus dk, this distance is delta k perpendicular. The difference between two orbits is dk, and now we have the following. So the area of this stripe, the area between these two orbits, can be found out by multiplying this delta k and dk, and integrating it over total. What we find is follows: EH, and including delta E as well, becomes ds. Now ds inside goes becomes dE in an integral sense, where S is the surface area of the stripe. So now we know T, and putting this value in omega c is equal to 2 pi by T, it becomes 2 pi divided by h cross square c. EH goes in the denominator and becomes dE by ds. So this becomes the angular frequency, and therefore 2 pi EH by h cross c ds by dE by ds. So the correct option becomes option 2, dE by ds. And following the same relation, what we can find out the cyclotron effective mass, in the sense that if one defines 1 by mc in the above equation, let me just pull this equation out. And in this equation, let us define 1 by mc to be 2 pi h cross square dE by ds. Then we have, because omega c in these terms is to EH by mc, so the rest of the terms we have are for the effective mass. So the mass becomes 1 by mc is equal to 2 pi by h cross square, or I can say mc becomes h cross square by 2 pi ds by dE, h cross square by 2 pi ds by dE. So this becomes cyclotron effective mass, and defined as follows. Now the next question is, which of the following conditions need to be satisfied to observe the oscillation of magnetic moment of a metal as a function of magnetic field intensity? Now there are two conditions for this. Basically these write two conditions for observing cyclotron resonance. First condition is that the mean free just a second, the mean free path of the electron to complete one full cycle should be large enough that it can complete its one full cycle. So in this time of completing one cycle, there should not be any collision. So if I multiply the collision lifetime between two collisions, that is tau, by the frequency, then this number omega c times 2 pi should be greater than 2 pi. There is the angle created by the electron. So this is the first condition to observe a cyclotron resonance, because if this condition is not satisfied, electron is not going to complete a full cycle. And second is that the cyclotron frequency in general is smaller than thermal energy. In general, cyclotron frequency is smaller than or cyclotron frequency or cyclotron energy analysis is in general is smaller than the thermal energy. So phonons are, there are greater possibility that phonons will scatter these electrons. So phonons will cause scattering. This means that the cyclotron frequency h bar omega c should be greater than the thermal energy. So we have these two conditions with us now, and therefore the option becomes omega c tau should be greater than 2 pi and the cyclotron energy should be greater than thermal energy. Now next we have is according to the Haas-1 effect, which of the following statements is correct? Now in the Haas-1 effect, magnetic moment varies inversely as proportional to the applied magnetic field. This certainly directly comes from the result of the Haas-1 effect. So magnetic moment varies, and also magnetic moment varies periodically as well. Periodically with function of magnetic field, it is a function of magnetic field, but it varies inversely. So the correct statement would be magnetic moment is related to magnetic field but as an inverse. Next is if the vector potential is given as A is equal to Hx times y, A is nothing but the magnetic vector potential. We know that the magnetic field is related to A by del cross A. Now cross product of these two can be simplified very easily. Ijk del by del x, del by del y and del by del z. A becomes 0, Hx and 0. If one simplifies it, all the components corresponding to I and j dies out because of the different dependence of variables. So only the k component remains, which is nothing but del by del x of Hx minus 0, which with respect to x only h survives k. And since in our options the unit vectors are given as k, so the unit vector corresponding to k direction is nothing but hz. So the magnetic field is given by h times z. Answer is C. So next question is, consider a free electron gas in a box of side Lx, Ly and Lz, and an external magnetic field H is applied. The number of states having the same energy is given by. Now to understand this, let me take an example here. So let us consider a 2D lattice. And now these are the k points in the two-dimensional lattice. Direction of kx and ky. Now as we know that when magnetic field is applied, the electrons in the solid starts to make orbital motion, starts making orbital motion, or kx ky plane goes into orbits. So And also there will be many states which degenerate for the cyclotron resonance frequency. And to draw these orbits, let me take the first orbit, example of the first orbit. There are some few points this orbit touches upon. There are some other orbits as well nearby to this, and there will be increase of points that this orbit touches. Let's say the first orbit corresponds to is L is equal to 0, L is equal to 1, and 2 and 3 and so on. Now it is very easily, it can be shown that the area between two orbits is given by 2 pi k del k, where k is the radius of the orbit. Now this is the same exercise that we used to do in finding the density of states calculation. So area between two orbits is given by k del k, and also it is known that k del k is given by delta E times m by h cross square. So this comes from the fact that E is equal to h cross square k square by 2m. Differentiating delta E would give us h cross square by 2m, 2k del k, k2 cancel, and we can rearrange it in this form, in this fashion. So k del k becomes delta E by mh cross, and putting this value, the area between two orbits is 2 pi, nothing but 2 pi m by h cross square times delta E. Now in the k space, number of allowed k points per unit area is given by the physical dimension of the material divided by 2 pi is a product of the two thing. Sorry, this will be x. So Lx Ly divided by 4 pi square. These are the number of allowed k points per unit area, and we have this area. So in unit area we have Lx Ly by 4 pi square number of k points, and in this area by unitary method we can find out total number of states would be Lx Ly 4 pi square into 2 pi m by h cross square into delta E. Now delta E, which is the energy of the cyclotron, can be written as h bar omega c, energy difference. In fact, this energy, this is the energy difference between two orbits. So pi goes with pi, and we are left with Lx Ly divided by 2 pi h cross square into m. Now h bar omega c can be written as E h by mc. M goes with m, and we are left with h cross square. H cross Lx Ly E h by now this is h cross, so 2 pi h cross is nothing but h by 2 pi into c. 2 pi cancel. Lx Ly Eh by hc. So these are the number of states in that region. Lx Ly Eh by hc. So the correct option is B. Now the energy gap between, the question number 9 says the energy gap between two degenerate energy levels of a free electron gas in an applied magnetic field. Now let's say we were in the situation when all the states of the system were occupied, and this axis is energy axis, and just this axis, let's say, let me just consider that the DOS. So initially all the DOS, and this is some finite or I can say that initial state, or let me call it H is equal to 0 state, that no magnetic field is applied, and the electrons are filled up to a certain level, which we know that is the Fermi level. Now these degenerate, now when applying an electric field or magnetic field, now on the application of magnetic field, these states merge together and become degenerate. So there is degeneracy coming up. We have some finite states. So all these states in this merge into single, all these states corresponding to this energy merge into one. But so let's say this is B1, and if we increase the magnetic field, then the difference between these states increases, and the effective difference between energy states increases. Let's say B2, and provided that B2 is greater than B1. So this is what we found experimentally, that on increasing the magnetic field, the energy gap between these degenerate energy levels was found to increase. So the energy gap between two different energy levels increases with increase in magnetic field. And finally we have the question number 10th, which says that according to the Friedel sum rule, the number of electrons added or removed by an impurity is given by which of the following option. Now we know that addition of impurity leads to generation of some new states in the gap, leads to generation of new states in the gap. Okay, and these new states generates or accommodates these additional impurity electrons, right? So also for each L, that is the angular momentum quantum number, we have the shift of del kf, that is the Fermi wave vector, minus delta 0, the difference. This is the phase shift for each L, and also for each L we have 2L plus 1 angular this magnetic quantum number level degeneracy, 2L plus 1, we have this degeneracy. So total number of electron that can be accommodated in the states created by the impurity by an impurity is given by, now since electrons have spins, so let us multiply it by 2, and since for each L we have this the phase shift, and for each L also 2 plus 1, so total number of states would be the product of these and given by the summation which runs along the side L, 2L plus 1 multiplied by del kf minus del 0 divided by 1, and the phase shift corresponding to k is equal to 0 vector, that is del 0, is very small because because when k is equal to 0, lambda, which is nothing but 2 pi by k, lambda tends to infinity, and when we have infinite wavelength, so phase shift corresponding to that wavelength are not significant enough and can be neglected. So total number of electrons becomes pi, from the bracket comes out, and we are left with L, 2L plus 1 phase shift corresponding to kf. So this this total number of electrons is nothing but the Friedel sum rule. So the correct option would be 2 by pi summation L 2L plus 1. So we have delta L of kf, 2 by pi, yes. The correct option would be B option. And in this way we have completed the solution for the assignment 8 for week 8. anything, one can unmute and ask anything. Any questions? If not, then we can park this present live session here.
Okay.
Is the present session fine? Then we can close it.
Yes, yes, no
Okay.
question.
Yeah. Thank you, and we'll meet next week.
Okay.